Yeah, I think we can start to open the webinar. So welcome everyone to the webinar series of iClimaBuild. And today we are going to listen to the presentation on the topic of fiber reinforced concrete. And the goal of this webinar is to present the innovation material and structural solutions as well as characterization methods concerning carbon textile reinforced concrete structures with a focus on facade elements. And yes, yeah, and we are honored to have the experts in this field from HTWK Leipzig and TU Dresden as our invited speaker today. And the first speaker is Professor Robert Böhm from HTWK Leipzig. He will give a short introduction on material efficient carbon fiber reinforced concrete panels as building systems. And then the next speaker is Daniel Wolz. He will present on lignin-based carbon fibers for novel reinforcement systems. And the third speaker is Lukas Steffen from HTWK Leipzig. And he will give us a talk on construction and calculation of lightweight carbon reinforced concrete structures. And the last topic is will present by Otto Grauer on the topic of the carbon concrete facilities for research into automated precast concrete construction. So now I think we can start with the first presentation from Professor Robert Böhm.
Yeah, so thank you, Nate. I will surely need to share my screen. So you have to allow this for me.
Now, Robert, you're able to share.
All right. So do you see my screen?
Yes, now.
Okay, fine. Okay, good. So good morning, everybody. Welcome to this second iClimaBuild webinar. My name is Robert Böhm. I'm Professor for Composite Materials in HTWK Leipzig at the Faculty of Engineering. With this presentation, I want to give you a short introduction into the material that we are investigating. All the details will be explained in the presentations right after me. So I'm gonna try to keep it short and only show the general ideas. So the starting point for our research is that we can observe that the concrete industry, mainly the cement industry, consumes very much CO2. Actually, the CO2 consumption of cement production is 3 times bigger than the worldwide CO2 emissions in aerospace. So basically, from the, let's say, climate protection perspective, concrete is a real evil material that we should try to avoid. And because this is well-known, these are well-known numbers, the politics already has changed something. So since 2020, there's a directive that says that all new buildings in the European Union should, that all buildings that are built new should achieve nearly zero emission consumption. And so phrase that is used for that is NZEB, nearly zero emission building, or nearly zero energy building. So, and that is also our vision. We currently see that typical, let's say, standard building lose a lot of heat. So you can see this on this picture above here. So they lose a lot of heat, and so they need to be provided with energy via energy net. And what we are trying to achieve by developing lightweight materials is that those buildings will lose less heat and can generate their energy for themselves. So what we're trying to achieve is basically autarky, or net independency. And in the best case scenario, we can think of scenarios where such a building generates more energy than it loses. And in this case, we might even use this energy, for instance, for electrical cars or something like that. And that is also the objective of the iClimaBuild project. Some of you may already know this. So this is the project we are all together working in. 27 partners from 14 countries are involved here. And so the major goal is to go the next steps towards nearly zero emission buildings. And within this project, there are many materials, many technologies are investigated, passive technologies to reduce the energy consumption of buildings, but also active technologies. That is the framework we are working in. And the material that we are investigating is, as already said in the beginning, called textile reinforced concrete. You can see this in this left picture here. So very thin concrete structures that are reinforced with carbon fibers. Those materials are very interesting also from the environmental protection perspective. But we have to say that lightweight materials, especially for buildings, they heat up very quickly, and they also cool down very quickly. And for that purpose, we need to have an insulation. And the insulation within our approach will be conducted by using so-called cellular lightweight concrete materials, CLC, which are additionally reinforced by aerogels. So the sandwich core that you can see in the right picture will be a multifunctional material. So, and that approach is already published 2 years ago. So to get a little impression into textile reinforced concrete, some pictures here on this slide. So we replace steel reinforcement by carbon fiber reinforcement. So this reinforcement can be either rods that you see in the picture on the left upper part of this slide, but also aerial reinforcement in form of mats. And those two reinforcements can also be combined. For instance, you see in this two pictures on the right, so a reinforcement combined by rods and mats, and then this reinforcement will be used to apply concrete for a structure, and you get such a product. So the right part is made of TRC, and the left part is made of steel, and you can already see that the TRC part is much thinner. Another main problem why we use TRC is that in conventional buildings with a steel reinforcement, we have to consider the fact that steel corrodes, as you can see in this left picture here. And when that happens, the structure cannot carry the load sufficiently anymore, and it needs to be subsequently strengthened. And when you want to strengthen such a structure by steel reinforcement, you again need a lot of concrete material, as you can see in this right picture. So here TRC is a very charming solution to avoid the use of concrete, and in this case also to decrease the CO2 that is released within concrete production. From life cycle analysis perspective, we can say that, as I said, by using TRC, we will save approximately 2/3 of cement, which also means that 2/3 approximately of CO2 equivalent can be saved. And we also use less sand, which is for the moment a big problem too. There will be a presentation in the end of this webinar about automated manufacturing. We are able, so the people in the consortium of iClimaBuild, we are able to produce such sandwich elements in a large scale automatically. For that purpose, we have built up a so-called pilot line, and this pilot line is able to produce structures in the dimension of many meters. How this works, again, already was published in this paper that you can see as a reference here on the slide. This technology is not a lab technology anymore. Such multifunctional facade elements are already used in buildings. For instance, in this building that you can see here in this picture. Within the research cluster iClimaBuild, the new sandwich materials will be tested within so-called living labs. For our materials, we use 3 living labs and 3 different climate zones. So one living lab that you can see on this picture here on the right is in Germany, and there are 2 other living labs in Spain and Italy. And those materials will be implemented into this building for long-term testing of the insulation properties. So to sum up my talk, this was, as I said, only a short introduction. This webinar will contain 3 more presentations that will follow my presentation. One presentation about the carbon fibers, one presentation about how to design such TRC materials, and one presentation about production. So yeah, this is the end of my presentation. Thank you for listening, and in the case you have questions, you might email me or also call me. Thank you.
Thank you, Professor Robert. So you have any question? You are allowed to ask from the chat or Q&A session. So if you would like to ask some question, you can raise your hand, and then I can allow the microphone for the audience. Yeah. If there is no question for the moment, I will move to the next topic. So the next one, yes, so it's from Daniel. So now I give you the floor. Oh, we cannot hear you at the moment.
Sorry, the mic was still off. Can you see the presentation?
Yes.
Oh, perfect. Then thanks again for having me here. I'm a research team leader of the TU Dresden in regards to carbon fiber conversion, and I will bring you today some specifics about lignin-based carbon fibers for novel reinforcement systems. First, I would grab the chance to introduce you first the Institute of Lightweight Design and Polymer Technology, as not all of you might be already know it. So we have a big institute working on all topics of lightweight design, polymer technology. We have about 80 young talents per year. We have 245 researchers, and within this Institute of Lightweight Design and Polymer Technology, we cooperated with the NASA Institute of the Technical University of Technology, the Institute of Textile Machinery, to bring the carbon fiber to new horizons. We created there the Research Center Carbon Fiber Saxony, which has the aim to develop precursor adaptive process designs for tailored carbon fiber products. So what we are aiming for is reducing along the process chain polymer fiber spinning, stretching to thermal conversion, fiber surface modification and validation, all topics to bring the carbon fiber to the specific applications they have to, and that we can overcome some challenges commercial fibers cannot do. So where's the Research Center for Carbon Fiber Saxony located? It is in the southeast of Dresden. Our main campus of ILK is in the center of Dresden, and also you can see the main campus. So why do we actually need novel renewable reinforcement systems? We at ILK and also at TUD and C-Cube and in this big consortium of iClimabuild think that the ecological cities will be made by renewable materials, and that the future of lightweight structures is resource neutrality. The question is, if we are looking onto something like this picture, there is a very much of biology, there is trees, there is green, but there is there is concrete. So we have concrete in the way that we have to produce it up to now, or still sick. As Mr. Böhm already introduced very nicely, we have the challenge by applying reinforcement rods made by carbon fiber to get there that the concrete will itself be getting lighter. So if we want to do a complete renewable system, then we not only have to make the concrete in new ways, we also have to do the reinforcement rods on new ways, because now it is on existing commercial synthetic oil-based production base. And the question is how we can make this carbon concrete more renewable, the reinforcements for the carbon concrete more renewable. The question is, how is this process chain actually looking? So we are starting by precursor fiber. We have afterwards the production of carbon fibers. After that, the fiber pultrusion will step in. And at the end, we have CF-based reinforcement rods, which will be applied in carbon concrete. That's the complete process chain. I will today speak about some aspects targeting every point so that you get a broader impact on the challenges we have to do. Starting with precursor fiber. So if you look in newest production forecasts for carbon fiber, we have up to now at 2020, 170 kilotons of carbon fiber production, meaning that we are at the range here. This is a Corona decrease which we had to apply, but now we are up again to 107,000 tons of carbon fiber production, which is forecasted for a tremendous increase. The thing is, if we have 107,000 tons of carbon fiber, we need therefore 214 tons of precursor fiber, as the carbon fiber itself has a mass loss by 50%. So this is just the forecast on the predictions we now have in regard to standard commercial applications. The question is how it is going with carbon fiber-based concrete or carbon concrete. So here you see a prediction by our in-house consulting, Mr. Jäger. There, the predictions go up to a CF demand in 2030 for 700,000 tons of carbon fiber with carbon fiber-based concrete. Meaning, if we are looking on the carbon concrete itself, we would need there more than 500,000 pun precursor fibers for carbon concrete. The thing is, if you look on nowadays production for synthetic and cellulose fibers on the right side here, then you see that we have about 90,000 tons of production. There are two things. There is not every polyacrylonitrile included in there because this is made internal, but we actually would have to increase the capacity by at least 5.6 times. Meaning that we would have to increase the polyacrylonitrile production in the chemical industry by 5.6 times, meaning that we would have a need of 5.6 times of oil. This can't be the solution for renewable and ecological cities. So the question is, why is polyacrylonitrile such a nice precursor? Because it has just a loss of 58%. If we are looking on the alternatives as renewables, we have lignin, but these just have a carbon yield of 20%, meaning that we are wasting 80% of the original raw material. Looking on cellulose, it is slightly better, where we have a carbon yield of 25%. Still, it is a decrease in the raw material efficiency. Additionally, we have there the challenge. If you look on this Gale permeation chromatography analysis, you see that we have there a very smooth distribution by polyacrylonitrile polymers, meaning that we are having less defective carbon fibers, smooth production. There is not very much difference. If you are looking on a raw material like lignin, this has much more broadenings in the polymer distribution, meaning we have to have there much more sensitive in preparation, fiber spinning, thermal conversion, up to application. So polymer distribution is still a challenge to solve for homogeneous precursor fibers to get nice carbon fibers. These are some challenges we have on precursor fibers. If you're looking on the carbon fiber challenges. Within this diagram, we prepared internally at RCCF. You see on y-axis the tensile strength, and then x-axis the Young's modulus. If you look onto this slide, then you see for 1 point the maximum elasticity, also the maximum extension, break extension for carbon fibers ranging about 10%, determined by Griffith's law. On the orange side, this is carbon fiber and on commercial and research way. If you look onto the lignins, we see that we have there much less possibilities developed as for application. Meaning, if we are looking into the requirements for CF reinforcement rods, then we have additional challenges to do. For instance, if we would like to replace a steel rod with 210 gigapascal tensile modulus by a CF reinforcement polymer rod with a 60 volume percent fiber volume percent content, we would need for tensile strength a barrier of 3000 megapascal to challenge. This is already achieved by lignin blend contents or lignin blend fibers from 50 to 80%. Still in the upper range, about 90%, 95% to 100% lignin, there is not a solution visible right now. Still, we have some solutions here which we could apply. But if you're targeting Young's modulus, there we have the thing that this barrier is not solved right now. So what we have to do in carbon fiber conversion is to bring new solutions to challenge this barrier, to apply and support the construction industry with new fiber solutions for this renewable carbon fiber reinforcement rods. So, but how we can challenge it? Looking on the typical carbon fiber technology we have there, we start there with precursor fiber, we go to stabilization, carbonization, have at the end the carbon fiber. So stabilization usually works in temperatures up to 400 degrees Celsius in an air heated convection oven, and 12 times between 40 to 180 minutes, depending on the manufacturer you have. The now standard of stabilization is in the range of 40 to 80 minutes nowadays, meaning less time to stabilize. If we look on carbonization itself, there we have two ovens, one for low temperature, one for high temperature. In maximum, it is going from 400 degrees to 1500 degrees Celsius. We have their nitrogen atmosphere to push out every hydrogen atoms, and the dwell times range between 1 minute to 10 minutes. But what is actually the difference between polyacrylonitrile and lignin? So if we look here on a polyacrylonitrile precursor fiber in the heat convection oven, we see there a very peak, a broad and a very strength and clear peak. Meaning in process regulation, we have the challenge to to avoid overheating and therefore fiber break, as this would meaning a complete loss of the precursor fiber. There is possibilities to do this broadening by additives like hydroxides, metacryl or vinylocrete to broaden this. If we are looking into lignin versions, I apologize for that. This is both in exotherm version direction, so you have to just change the slide. Then we see that we have there much smaller exothermic reactions, meaning we can not only broaden the polyacrylonitrile peak, we also have diminished exothermic reactions, as already a lot of oxygen is within the polymer itself. Meaning via lignin we can reduce exothermic reactions and have therefore enhanced process stabilities. Still, if we look on polyacrylonitrile precursor fibers, we see there we start with increasing temperatures and increase in Young's modulus over the complete time. In the state of the art, this has not been proven for lignin and cellulose carbon fibers yet. So still there is a challenge between we can achieve here up to 500 gigapascal and polyacrylonitrile precursor fibers. The actual state of the art for lignin ones is 100. In this publication, it has been 67. Also, if you're looking on tensile strength, I'm sorry, here are the mistakes. This means to be a 4. We have there tensile strength up to 4 gigapascal, while we are maintaining at lignin but at 1 gigapascal. So we have there complete different temperature dependent tensile modulus behaviors, which have to be solved out in future studies to bring renewables into carbon fiber. If we are looking on the manufacturing afterwards on fiber pultrusion, we have there the thing that we need polymer reinforcement rods by fast process technologies. At ILK, we developed in cooperation with partners of C-Cube a pultrusion process where we have a first coil rack, afterwards the CF tape collection, a collection nozzle to bring them in together, the heating device, cooled molding device, afterwards the CF reinforcement rod, and air cooling and discharge equipment. I now hope the video will work smoothly. So what you see here is the collection device with the CF tapes, the heating device to heat up the carbon fibers, the cooling device and the molding device. This is the molding device where the polymer matrix is applied on. Afterwards, the cooling device and the pultrusion of the fiber reinforcement rod itself. So this mechanical pultrusion is needed for, so if you look on steel rods, then you see that there is bulges for enhancing the mechanical stability. This has been also done at the invented carbon helix rods by the pultrusion process itself. Here you can see the nozzle where the pultrusion is done in situ within the process by pultrusion of the carbon fiber polymer rod. If we look into this rod, this is a computer tomography. You can see that the neutral fiber line is still located at the same position, even if the outer barriers are changing. This little smooth point is polymer rich region which you not see in the computer tomography analysis. So we can build with this pultrusion by the nozzle a carbon fiber rod where the neutral line is still having always the load barrier, the load bearing function in the same direction, but while the outer points are diverting. Still, the question is, can also renewable polymer matrices be applied? Yes, they can. We have there multiple possibilities about lignin-based thermoplastics, lignin-based epoxies, which will be future points of study and which will be future point of studies. Still, at the end, we have to bring in the reinforcement rods into the carbon concrete. Therefore, different spacers, extruded pin connectors, flatline spacers has been developed to maintain the application processes at the construction locations by the same like reinforcement rods. Additionally, we have to build their anchors, which have also to be performed or to be manufactured within the systems we have. Therefore, forming and bending station for carbon rods has been developed with forming aids or rotary pressure bending devices, producing the anchors we need to combine or to combine the different reinforcements for the rods. So the question is, we have several challenges at every station to solve, but there are already series concepts to do it. The question is, can the concept for full renewable carbon fiber reinforcement bars be pioneered? We think yes. We are targeting to do this in the future studies. Thank you very much for your audience, for our consortium, as well as for the audience. I think that we believe that the future of lightweighting is resource neutrality. Therefore, we forwarded our Dresden model of lightweight design to the advanced Dresden model of neutral lightweight design. I thank you very much. I thank you, my pre-speakers and my after-speakers. If you have any questions, please contact me and I'm happy to answer your questions.
Okay, thank you, Daniel. So is there any question you can ask?
Yeah, I have a question. There is a EN standard for these rods, for carbon rods, like we have in steel.
Yes, there is by construction laws. There is so you have to have 210 gigapascal tensile modulus, depending on the so the size is depending on the right legal institutions norms. I'm no expert in this. We just put this as example to replace reinforcement, so a steel rod like it is used nowadays in the construction industry.
Yeah, I was meaning more on the material side, that for the steel reinforcement, you have like a way of the rib pattern, so it's something standardized that every producer can follow up. And so if you are patenting or you have some patent on this helix rod, so if this is something that, because I mean for the market, maybe it's a problem to like use this bars.
Yeah, it's still a little bit of a challenge. There is, I have colleagues at my institute, so I am carbon fiber expert to say. The construction experts could give more details on that.
Okay, thanks.
Any other question? I have a common question. Like I would like to compare the price between the steel bar and the carbon fiber reinforcement. Like, do you give the rough number, like with the cost of production or like the price that sells?
Price discussion is a difficult thing because it is, as always, a point of where the demand and how high is the production capacities. If you would now calculate it, it would be more expensive than steel. We don't have to question this. The question is, is there a need in future for it? We think yes, because concrete should be less used to have more resource neutrality. Carbon dioxide prices will increase. They will increase a lot. So the question is at the end, a price optimization. I have to say we didn't calculate it now. Still, this pricing is a difficult question about how high are the production capacities and how high is the demand. Then there will be a solution.
Okay. Okay. Thank you. Okay. If no more question, then we move to the third presentation. So Lukas, Steffen.
Yeah.
Yeah, you can share your screen. Yes.
Okay, perfect.
And thank you, Daniel.
You're welcome.
Can you see my screen?
Yes.
Okay. Okay, perfect. To my part, that's construction and calculation of the lightweight carbon reinforced structures. I'm from the HTWK in Leipzig and from the research group for sustainable buildings. Yeah. So why we need to change something in our
Sorry, Lucas. We cannot see in the presentation mode. Can you put it in the presentation mode?
Oh, okay. Wait a second. Oh.
Yeah, in the lower.
I need to see. Here. Yeah. Okay. So, is it fine now? Is it in the presentation board?
Yes. Thanks.
Okay, perfect. Thanks. Yeah. So, why we need to change something in our construction is mainly that by only 10% of the, so that's the numbers for Germany, by only 10% of the GDP and 7% of the work value or the human resources, we use up to 50% of the resources and 40% of the energy for construction, and produce 60% waste and need 70% space for our construction. That's a problem because the industry is really wasteful at the moment, and we have to do something to stop it or prevent it, or have better solutions to reduce the amount of resources, energy, and space and waste that we are using to construct our buildings. How we can do it? The main goal is to reduce the CO2 output by 2045 to zero carbon emission. And one main aspect is that the building industry or the construction site have to reduce this CO2 output, and we think one solution for that is the development of carbon concrete that is now market ready since 2002. And if we use carbon concrete and we think the market share will rise, we will reduce CO2 output. And I think that's a good start to get the goal to zero emission in 2045. Here you can see the development of sandwich elements. So on the first picture, you can see a normal reinforced concrete, so it's with steel reinforcement, and it needs a lot of space. A bit like this, and it's got also in situ core. And the first step was to change the outer shell, so the weather shell, to carbon concrete. So there we can reduce the thickness by 4 centimeters. So we only need half the concrete for the weather shell. And in the next step, we use the load-bearing shell and use also carbon concrete for this one, but we still need the in situ core. And the last step was to change the isolation to aerogel isolation from BASF, and that's called slantite. It's a silica isolation, and there we can reduce the thickness of the wall by 20 centimeters, as you can see. So that was the first development of the carbon concrete sandwich elements. Now it's only for Germany, but now we have, since this year, we have one guideline to build with non-metallic reinforcement. This guideline is for all non-metallic reinforcements, so glass fibers, carbon fibers, and so on. But it's the first standardization for building with non-metallic reinforcement. But at the moment, it can only be used in Germany. But yeah, I think soon it will come for the European Union, and then it's the first standardization to build with non-metallic reinforcement. Here you need a model like, or a sandwich element like this one is a cube. So you can see it on the left side with an in situ core. The model for the static looks like this. So we have a weather shell on the outside where we got the external forces like wind and stuff like this, and we have the inner shell that's for load bearing. And here we can't use the anchors or something like this, so we can't use the outer shell for load bearing. It's only the facade or the weather shell. So on our model for the statics looks like this. We have our dead load and our external forces plus the dead load from the weather shell. That's not an issue. We can calculate it really simple according to the first order analysis. We only have to apply an external momentum for the weather shell. It's simply the dead load times the spacing between the two shells. And there we only have compression in the in situ core and only tension in the carbon concrete panel. So therefore the carbon reinforcement is fully utilized. And yeah, but the calculation is like a simple steel reinforced beam, I would say. So it's a simple calculation, but with the in situ core we can improve the behavior, and we don't need like high pressure performance concrete for the in situ core. It can be done with a simple normal concrete because the zone is really high. So also load bearing can be done with less effective concrete. For iClima, we have a different model. We don't have an in situ core, we only have two shells, so a sandwich element with anchors. Here we got the same problem. We have our model in the middle, but for our statics, we can only use the load bearing shell and not the weather shell. And here you can see we only have the 3 centimeters to vary all the load from the external forces and from the dead load. For the living labs and iClima, that's, yeah, we also have the force from the weather shell, so the dead load times the spacing. It's the same with the in situ core. But for iClima build for all the living labs, it's fine to calculate it like this. The problem here is, or it's not a problem, it's, yeah, you have to consider it. The reinforcement is not for any load bearing or something like this, because it's in the middle of the 3 centimeter slab. So we have compression and tension only in the concrete, and 0 forces in the reinforcement. So we don't really use it for the load bearing effect, but we use it to have the ductility from the concrete, because if it gets cracked or get brittle or something like this, you need the reinforcement because otherwise it could happen that slabs from the concrete fall out and harm people. So we need minimum reinforcement. The calculation for this, and the calculation I done for iClima, is simply like a stone plate. So the main factor for the stability is the tensile strength of the concrete. One problem here is buckling, but we proved in the simulations that buckling is not a problem with the anchors and the weather shell, because we reduce the spacing between the anchors, and only spacing between the anchors can buckling. And for iClima it's fine, but it's not standardized. So yeah, the calculation for the stone plate is standardized, but not buckling. Yeah, as you can think, it's not effective to calculate it like this. A better way is to use your sandwich effect and place your anchors in a different angle. So we can build something like this one on the left side, on the right side. So you have a classic truss that we can build in. And with this method, we have a new system. And now we can use both shells for load bearing. Because on both carbon concrete slabs, we can put compression forces and tensile forces on it, and our anchors give us spacing and stiffness for the system, so it gets much more efficient. The main reason for this is that we utilize reinforcement to its full potential. The problem here is it's not standardized, so we can only do it in a simulation, and it's a little bit complicated because we have a lot of forces, a lot of tests we have to make for the anchors, for the slabs and stuff like this. So that's still in process, but that would be the next step to build something like this that we use it to the full potential. So here's a little overview for you to see what does it cost, or when does it be worthwhile. So for the normal standard double wall system with reinforcement, steel reinforcement, we have a cost by 150 euros per square meter, with a wall thickness by 44 centimeters. For what we do at the moment, or what is standardized, is for example, here's a cube wall. It costs more than double the cost, but we can reduce the thickness of the wall by 70 centimeters. It has the same properties, so same isolation properties and same load bearing properties, but it's double the cost. When is it worth? Here you can see a little calculation. So for the normal wall, for the cube elements, we have a height from for 1 meter wall with a height of from 2.7 meters. We have a cost for 675 euros, and the same wall in the cube costs 1,190 euros. That's the difference for 550 euros, but we reduce the space, or the space gained with the smaller walls is 70 centimeters. So if your cost of your land you will use, or your area cost is more than 3,000 euros per square meter, it's more efficient or more economically useful to use carbon concrete walls. But it's only for the spacing. So you have other factors like you can have less transport costs and stuff like this. So it reduces it a little bit. But yeah, so 3,000 is a mark where it's worthwhile to use carbon concrete. If we use the carbon concrete or as a system in the cube, we have up to 7% more marketable area, less construction area, up to 35.6%, and our transport weights are up to 42.8% reduced. So that's all factors that are good for the carbon concrete double system. If we look at the economical factor for the fibers, here you see reinforcing steel, stainless steel, glass fibers, and carbon fibers for the CO2 equivalent. At the moment, for 1 kilo material, reinforced steel is that don't need so much CO2, or the production needs less CO2 than glass fibers or carbon fibers. But if you consider the density of the material, so you consider density, you use less material to get the same effect. You see it's drastically reduce the glass fiber and also the carbon fiber. So now we are close to stainless steel with carbon fiber, and now and for glass fiber we already have less CO2 emissions than reinforced steel. If you put in the consideration the tensile strength for reinforcing steel and tensile steel, it's 500 Newton per square millimeter. For glass fiber, it's 1000 Newton per square meter. So you halve the CO2 output, or you halve your use of the reinforcement. And for carbon fiber, it's 2000 Newton per square millimeter. Therefore, you only need 1/4 of the carbon fiber compared to reinforcing steel. If you use high performance carbon fiber, it's like 4000 Newton per square millimeter, you halve it again. So now, if we consider this, we have more than 50% reduce of the CO2 emission in our reinforcement for our carbon concrete. Yeah, here you see some pictures where we use it in the cube in Dresden. I focus here on the box that's darker. There's a darker walls in the front here. Here's a picture from the inside. So that's the walls I talked earlier about, the 2.7 meters high, and are built in the facility. Here you can see the construction of the walls. There we lay down 1 centimeter of concrete, put in the reinforcement nets, and then again put a 2 centimeter concrete on it. So that's our first slab. You can see it's all done by hand, so that's mainly the reason why the costs are so high. And yeah, the next step is to get the isolation on, and then we put the anchors through the isolation into the concrete. And of course, the last step is to build the last slabs. Here, the spacing between the isolation and the last slab is for the in situ core, because that's what we need to build like this. Here in the last pic, you can see the assembling of the elements. You can see they're really big, but we can build this big because we have to space it into the lorries, but the weight is not a problem, so we can use smaller cranes and assemble it really fast because we don't have like heavy elements. Yeah, that was my part. Thank you for your attention. And do you have any questions?
Thank you, Lukas. Anyone wants to ask?
Yeah, I have a really nice presentation, Lukas.
Yes.
I have one question about iClimate build and the panels. You will test this solution, this truss solution, to know how it will work.
Yeah, we planned a 4-point bending test, and there we will use normal spacing from the anchors from iClimate that we already built, and there we will test 3 to 4 samples of it, and to see if there's any effect from the sandwich load bearing effect. There will be a little bit, but it's not optimal. So we also will test it like the anchors in different angles, and therefore we do a simulation, and then we will test it in real life and see what we can improve for this type of elements or this type of walls.
You will use the same type of connectors, but
Yeah.
inclined? Okay.
Yeah, HTWK, like that.
No.
Yeah, the main problem is it's from Stöck. That's where it's produced. It's glass fiber anchors, and they only can, or it's only allowed to build slabs by 4 centimeters. So all tests are done with 4 centimeters, and in ICLIMA we use 3 centimeters carbon concrete. It's better to use 3 centimeters carbon concrete because we can reduce the thickness, and so we can reduce the CO2 output. But we have to do additional tests to test the anchors in different angles, and for the 3 centimeters, and then we can do the simulation, and then we can build big models or big demonstrators to test the 4-point bending effect and see what difference it will make. But I think it will be a big improvement to use the anchors also for the load bearing, and to use both shells as load bearing.
Yeah, I think
slabs. So
you will increase the bending moment capacity, because
Yeah.
somehow half of the only if you transfer half of the load, then it will be quite an improvement.
But for ICLIMA at the moment I calculated only as a stone plate, because you have to consider
on the
the
safe
safety
side.
of the worker. It's on the safe side.
Okay,
So we
thanks.
don't want to risk anyone.
Thanks a lot.
Okay. So now we move to the last presentation of this webinar series. It would be Otto. Yes. So I give you the floor.
You see my presentation?
Yes.
Okay, then thank you very much for the introductory words. My name is Otto Grauer. I'm a research associate at the Institute for Concrete Construction at the HTWK Leipzig, and I'm also the head of the Carbon Technical Center in a little bit louder. Sorry. The head of the Carbon Concrete Technical Center in Germany. Some steps to me. I studied civil engineering, and I have been working intensively on construction robotics for the last 7 years. The focus is primarily on the automated production of carbon and also textile reinforced concrete elements. So today I would like to give you the results, the research so far, in a short excursion at the Carbonbetontechnikum Deutschland, short CBT, and the topic, the Carbon Concrete Facility Germany for research into automated precast concrete construction. Within the far-reaching research, the goal has been set to replace approximate 20% of steel reinforced concrete with carbon concrete. To achieve this goal can only be achieved, since this goal can only be achieved by advancing the automation of the production of prefabricated and semi-prefabricated concrete parts. So the idea of initiating the carbon concrete model factory was born in 2019. And in the future, this will be used to implement a fully digital demonstration production line that is unique in the world, and will enable the digital, fully automatic, and thus highly efficient production of prefabricated and semi-finished parts made of carbon reinforced concrete. I'd like to explain the general structure of the CBT in more detail. Beginning with a few basic pieces of information. The technical center has a floor area of 1,200 square meters. It's equipped with a 20-ton crane. Furthermore, a clamping field in this area with a dimension of 20 to 6 meters is integrated. And we are currently working within 6 industrial robots, which they will do. I will give you some information later. Yeah, and I will talk about this in more detail in the next slides. Technical center is divided in 2 large areas. The model production line in area 1 is installed on 450 square meters, on which the automated production steps for carbon concrete are developed, examined, and validated. The possible component size that can be handled by the technology during the investigation range from 10 to 10 centimeters continuously up to a maximum size of 1.25 meters to 3.5 meters. A maximum weight of 2 tons can be transported by the tables. In terms of structure, the plant layout differs from the majority of exciting precast concrete plants. These use the pellet circulating system. The model factory was divided into 3 parallel working lines, each with 3 to 4 workstations. The changeover between the separate lines will take place here and here via 3 cross-travel units. The plant layout describes great flexibility that makes it possible to carry out development work on individual processes. Steps without endangering the operation of the entire plant. Currently, 4 workstations can be operated by robots. You can see here, and this robot takes 2. These are also the core work steps in the production of carbon concrete elements, production of the carbon reinforcement on the right side, production of formwork for thin wall elements, and for the formwork, it's the second one. Also the laying of the carbon reinforcement into the concrete, automated finishing and assembly, the last robot. Connected to the production line is a high-performance mixing plant, as well as a concrete distributor adapted to textile reinforced concretes. In addition to the model product line, the carbon concrete CBT has another 340 square meters of space for component testing. For example, test frames up to a height to 3.50 meters can be installed on a clamping field. I said it, 20 to 6 meters, which are used for load tests on larger components. Several climatic rooms and chambers are also here, and it can be used for specimen storage, water storage, and so on. But it's also for endurance tests under defined climatic conditions. Now we start with different stations. The first one, the automated yarn deposit and thermal post-treatment. At this processing station, the desired reinforcement structures are produced fully automatically in 2 and 3 dimensions. At the beginning, specially developed software automatically calculates the reinforcement geometry for our goal element for the respective component, which is then converted by algorithms into a laying part for the robot. With this information, the robot independently places the reinforcement on a tensioning frame. Here you see the tensioning frame, the turning points. During this yarn placement, the carbon yarn is impregnated online with a resin matrix. This binds the individual carbon fibers or the filaments together so that the complete reinforcement cross-section of the yarn used can be applied in the static analysis. In addition, the impregnation supports the position and the stability of the reinforcement mats during concreting. Once the reinforcement has been completely deposited, the clamping frame get together with the reinforcement is fed to the thermal post treatment here. For this purpose, it moves independently within the model factory to the next process step. In a circulating air oven, the scrims is subjected to a thermal post-treatment regime or tempering for the composite units specific to the resin. Here we use an epoxy this time, but it's also possible to use other resin systems. This determines the final strength of the resin matrix as well as the point of glass transition temperature. This is of great importance, course, for the subsequent use in the components and for the duration of the fire resistance. After the tempering process, the standard frame with the now curled fabric leaves the oven for the next processing steps. This next processing step is the automated formwork, laying, and reinforced placement. To the beginning, the automatic formwork laying. Yeah, this process, one of the two further process stations, is used for the full automatic production of the concrete formwork and the subsequent laying for the reinforcement into the formwork. Both stations can be operated by one robot by using a pneumatic quick change system. The robot is able to switch the fully automatically between different grippers and other processing tools. So it's very good for our research. In order to lay the formwork for concrete fully automatically, the geometry for the formwork is first generated by a specially developed element algorithm. This assembled the desired geometry from 5 magnetic formwork elements of different lengths, so that the formwork elements which are specially produced to use with textile concrete components can be adapted in shape. To make this possible, the chambers of the outside of the components were reduced. This, yeah, here you see it. Sorry. Yeah, reduced, and the height of the formwork elements was limited to 5 centimeters. In steel concrete, is 5 millimeters. In steel concrete, this is 1 centimeter, but it's too big for textile reinforcement elements. In addition to currently available shuttering robots, the use of 6-axis robots enables the simultaneous insertion of magnetic bar anchors on the vertical sides of the shuttering. These are needed to provide insurance or anchorage points with the components are lifted off later. A first partial concreting is necessary for placing the reinforcement. This has the advantage that the defined height for the placement of the reinforcement is achieved by placing a first layer of concrete, including compaction by means of preparation. The concreting is carried out with the help of a high-performance mixing plant. I will show you later. That has been further developed to fine-grained concretes, including a concrete distribution portal. The carbon layer is applied on the first, I say base layer of concrete. Another cribbing tool is available for the purpose. This is equipped with several 2-jaw grippers that can be adapted to the reinforced grid. Here you see it, it's the little ones, and on this tool there are 10 of these. So these grippers have a special, I say, pads on the gripper jaws so that no transverse force of introduced into the reinforcement stands during gripping, thus maintaining the freedom from damage of the reinforcement. This process step is handled by the same robot as for the formwork deposit, made possibly by the aforementioned quick system or quick change system for the tool. In the course of future investigations, further work steps can be added to these two process stations, since the tool change generally allows infinite number of processing and cribbing tools can be used. That's also good for our research. The next step, the mechanical finishing and further processing. Another special robot you can see here is available within the model factory, which can carry out finishing tasks in 3-dimension space. This is equipped with a high-performance turning spindle and can drill, grind, and mill individually as required. In this way, undercuts can be milled on the example of a curtain wall panel made for carbon concrete, where fasteners or so on, such as anchors, yeah, all these things can later be attached. Furthermore, it is possible to produce special formworks of elements by milling with the help of robots, for example, especially in the case of curved components, which can be produced thanks to the positive properties of the carbon concrete. The fully automated workflow allows the concrete formwork and the carbon reinforcement to be perfectly matched. The next station is the removal and the removal station. That's it. Rarest methods are used to remove a finished carbon concrete component from the production line. Either the formwork table can be moved onto a tilting table, which automatically fixes the formwork with the concrete component, securing against tilting in the upright position in order to be obtained the travel clearance for this tilting process of the tilting station. The component is moved into a vertical position. The crane tracks the sliding means are attached to the component integrated fastening anchors, and the component is transported by crane. I say maximum crane to 20 tons into a storage rack, and then it can go to the construction site. This procedure is necessary because contrary to reinforced concrete, lattice girders can no longer used as attachment points in the case of double walls. Alternatively, the connection means in the form of plastic pins are now used. They cannot be used as an anchor point for the crane, as they would cause too high bending stresses at the point of the total surface of the now gradually reduced thickness slab. 2 to 3 centimeters, for example, which would result in the damage on a slab. Sorry. Alternatively, it's possible a vacuum suction frame is available in this technical center in CBT, which can be attached to the rust surface of the back of the panels by means of special suction plates, and can thus move panel weights up to 750 kilograms. The vacuum suction frame can rotate the plates around all axes after removal, which simplifies handling for the next processing steps. Here, the last thing is a high-performance mixing plant. And it's currently being installed, which has been specially designed for our fine concrete. The current high is 9 meters, so we have 10 centimeters to the crane, and with 4 supply containers of 4.5 square meters for each, and an output of 30 cube meters. Sorry, not square meters. Cube meters concrete per hour. A distribution portal is also being installed, which is specially designed for a low drop high. Completion of the work is expected in the last quarter this year. Yeah, this was a short briefing inside the CBT and the model factory. I hope it was, I was able to show you some interesting things and new informations, and I'm at your disposal for any questions. Yeah, my name is Otto Grauer, and I thank you very much for your attention.
So thank you, Otto. It's very interesting. Is there any question from the audience? Nope. Okay. So thank you very much for all the speakers today. We are really appreciated to listen to the new technology and fiber reinforced concrete. And but before we leave, I would like to promote not this one, sorry. Yeah, we will continue the webinar series. To the next topic is it's about structural glazing and functional coating for BIPV application. So this is the next webinar series, and it will be held in October, 10th of October. So a few months after this, but please stay tuned. And our invited speakers are Dr. Sophie and Dr. Bruno from Fraunhofer, Germany. And we will open the registration in 17th of July. And please follow us on iclimabuild.eu. You can follow us from Facebook, Twitter, and LinkedIn. So now I would like to thank you everyone for joining our webinar of iClimaBuild, and see you next webinar series. Thank you.
Thank you.
Thank you.
And have a nice day.
Bye-bye.
Bye.